So let me first recap a little bit of what happened last time. So we introduced the notion of what it means for an affine scheme over a ground field K. So this ground field is always assumed to be algebraically closed of characteristic 0. So when I say scheme, I will mean a derived scheme, and we will always be talking about derived schemes of what I call almost of finite type. So let me not go into the definition of that. So we defined what it means for such Fs to be quasi-smooth. And what it meant is that if we take its tangent fibers, so they will live normally in non-negative cohomological degrees, and we want that so these cohomologies be 0 for I greater than 2. So in this case, we can define pointwise support of coherent sheaves. So if F was a coherent sheaf, and again, when I say that, I mean it's a bounded complex with coherent cohomologies. So, and S is a point, so we defined the singular support at S of F as follows. So we said that in our circumstances, the algebra, commutative algebra, sim, of the first cohomology of our tangent fiber acts on, viewed as a graded algebra, where the generator sits in degree 2, acts on this graded vector space, and this is just the support. So it's support of this graded module over this graded algebra.
So your whole algebraically closed field characteristic 0?
Yes. And so the support lives in the vector space dual to the vector space of which we took the sim. And so it lives inside, so, well, take H1, the tangent fiber, dual, i.e. it's the minus first cohomology of the cotangent fiber. So that was our pointwise definition, and as Lumon asked, so how do you ever get a handle on this? It's so theoretical. But so in a minute I'll give you kind of a couple of practical definitions of this thing. Let me just finish this recapitulating the story. So we defined a classical scheme, Sing of S, to be spectrum over the classical scheme underlying S, so kill all the lower cohomologies, spec sim of H1 of TS. So this is the tangent sheaf. You consider it's H1, it's a coherent sheaf on the classical S, take its sim. And so set theoretically, that looks like the union over all points of these guys, of minus first cohomologies of the cotangent fibers. And then we said, okay, so we have these pointwise supports, so to F we can assign singular support of F, which is a subset in the Sing. So the proposition is that it's closed. Is Zariski closed? So in the next talk, I will give yet a different definition of singular support, which will make such claims obvious. So for now, I'm just stating it. And so there was one essential result that I quoted last time that said the following, that so the singular support of F is contained in the zero section if and only if F is perfect. So singular support really detects the measure of imperfection of S. Okay, so now consider an example and a very kind of hands-on definition of singular support, and then I will give yet another definition of singular support. Okay, so here's another example. So let U be a smooth variety equipped with a function, and say this function is non-zero. So let's take the zero set of this function. So this is it's a hypersurface, and it's given as a complete intersection. So this is a classical scheme, but it's also quasi-smooth derived scheme. We said last time that locally complete intersections are exactly those quasi-smooth derived schemes that happen to be classical. So let's say in this case what sing of S looks like. Well, I gave a general criterion, well, general description of sing S in these circumstances. So we're looking at the, well, co-differential of this map. So it's kind of df star. Of course, the cotangent bundled to A1 is A1. So this is really a map from OS into this vector bundle. And it's the kernel of this map. i.e., it looks as follows. So at a given point, it looks as follows. It's 0 if df at S is not equal to 0 and is one-dimensional if so the function is degenerate at this point. And there is not much room for singular support. Well, according to this theorem, what you have is that, well, all I can say is just to restate this in this case, that singular support at a given point will be 0 if and only if F is perfect on the Zariski neighborhood of this point. So in the case of hypersurfaces, singular support is either 0 or everything.
So you mean it will be 0 or empty, because you can say 0. It is empty.
Yeah, for 0 we discussed this last time.
Okay, let me say non-zero. Be non-zero, and then if and only if is not perfect.
Hold on, is the empty set?
No, so non-zero means that excluding empty set and 0. I'm saying that you will hit this k if and only if you actually are imperfect at that point. Imperfect, 0 is perfect. All right. So now what I want to generalize this example, well, to a general situation. So we said that in general a quasi-smooth scheme can always be fit into a Cartesian square where U and V are smooth classical schemes. So the Cartesian square is taken in the derived sense. So, and parallel to this, so sing of S is the kernel of the map from T star V restricted to S to T star U restricted to S. So this is the dual of the differential. So I want to give a criterion, and let's notice the following. So let me introduce a piece of notation. Let me call the straight V the tangent space to this curly V at the point. And so what you see is that this always sits inside V star times S. So very concretely, the singular support will live in the S times the dual vector space, well, to the cotangent fiber to my V at the point. So now very concretely, I want to say when an element here belongs to the singular support. So let me take psi, an element of V star, and want to say when a pair S comma psi belongs to the singular support of a given sheaf. And so here's the procedure kind of that is due to Drinfeld, and you may, so there's some vague analogy with vanishing cycles. So its analogy is really vague, but well, okay, so here's what you do. Well, here, let me rewrite this again. Now choose a function on this V whose differential at your chosen point is psi. So this is my H and this is my F. So df at my point is psi. Okay, and so and vanishes at the point. So let me denote this by V prime. Let me denote this by the preimage by S prime. So this was my old point, and this is my S. So if you wish, S was the set of zeros of the map H, and S prime is a much larger closed subscheme. It's the set of zeros of the composed map.
H, there is no, what are the hypotheses on?
H? None. Absolutely none.
O and V are just smooth.
Yeah, the two guys are smooth and H is absolutely everything. Yeah.
And those guys are derived.
No, you mean these guys?
No, the S prime and S are derived.
So S and S prime are derived. Well, but in fact, yeah, both guys are derived. But note, however, that S prime is a hypersurface, because S prime is zeros of this composed map. It may happen that this map is zero, but it's okay. We're still, in fact, when we discuss this hypersurface situation, it's just as well applicable to the case where the function was zero.
Why not explain things like in coordinates? You get just collection of functions and some coordinates. You know, it's abstract notation. So it's complicated diagrams. Simple things complicated.
Let me do it, and then maybe I'll let you do it, because I'll get confused when I write coordinates. But okay. So all I mean is just create this diagram, and S prime is the hypersurface. Let me denote this closed embedding by I. So, and here is the theorem: is that so this belongs to the singular support if and only if the following happens. So you had your coherent sheaf here, take its direct image, you get a coherent sheaf here, and what you want is that this guy be imperfect. So, pardon? In the neighborhood, yes. So it belongs to this. If is not perfect on S prime on the Zariski neighborhood. So if you regard perfection as an analog of the property of elliptic sheaves being least, then you can detect singular support by this property, but not on the initial scheme, but on a kind of a bigger guy, the hypersurface.
High-lower stuff can, in the derived things, can be complicated? Or?
No. It's no complications here. It's just under closed embedding, nothing happens there.
So it's kind of, so it's a morphism of spaces with a DG differential voided ring, something like this.
Yeah, but it's direct.
You take that's the naive direct image.
It's absolutely, yeah. It's direct image is direct image. It's to have a map of rings, and it's a forgetful functor.